This is section 11.4, trigonometric, also known as polar, form of complex numbers. I will probably call them polar form most of the time. So, when we talk about complex numbers, that's the biggest set of numbers you've probably ever been introduced to. And any complex number is a number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary unit. And you may have seen this before, and that I was chosen to represent the imaginary unit where the imaginary numbers come from being able to take the square root of a negative number, which for real numbers you cannot do. So the square root of -1 is what I is. So I here is not a unit vector. It's a number. It's an imaginary number. And so any multiple of that, like 2i or -8i or whatever, those are all imaginary numbers. And that's a big set of numbers. In fact, there are infinitely many of them. For every real number, put an I after it, and you've got an imaginary number. So if we were to want to set up a plane where the real numbers were on a real number line, so that would be 0 and 1 and 2 and 3, etc. And then if we were to draw another axis perpendicular to that axis and go through at 0, we might consider that number line to represent the set of all imaginary numbers. And so the first mark on that axis would be I. The next one would be 2i, 3i, 4i, down below, opposite of I, -2i, -3i, -4i. And then, of course, the real numbers continue in the negative direction as well. So -1, -2, -3, -4. And so this, what we've just set up, is called the complex plane. And it contains all complex numbers. And every number that can be graphed here is a complex number. For example, this one, which has a real part of 4 and an imaginary part of 1i. So that number is 4 plus I, and it's represented. It's not a real number, so it's not on the real number line. It's not an imaginary number, so it's not on the imaginary number line. It's in the field away from those two axes, and it's at a place where the real part and the imaginary part are both represented. And so, as I said earlier, anything writable as a plus bi is a complex number. So my question is this: what about that number right there, 2? Is that a complex number? Well, if it's writable in the form of a plus bi, yeah, it is. 2 is writable as 2 plus 0i, and what that implies is that all real numbers are also complex. So all the real numbers are part of an even bigger set of numbers, the complex numbers. And what about a number like this one right here, 3i? Is that also complex? I know it's imaginary. Is it complex? Well, we know it's complex if it's writable in the form of a plus bi, and 0 plus 3i fits the bill. And so that means that all imaginary numbers are also in the set of complex numbers. Now, what we will do sometimes is represent these numbers as vectors that terminate at that spot. And so let me draw vectors for the 3 that I did already. And so we can represent the complex number graph as a vector to that spot where it terminates. So if we think about some arithmetic with complex numbers, for example, if we were to think about, well, what is the sum of 6 minus 2i and negative 4 minus 3i? Well, if we think of it like vectors, it's kind of like the horizontal component part would be the real part, and the coefficient of I would be the vertical component, and when you add, you just add like components. So we'd add 6 and negative 4, and we'd add negative 2 and negative 3, and put that in front of I. So this would be 2, and then negative 5, or so minus 5i. So in other words, you're just collecting like terms, where the real part A adds to A, and the imaginary parts BI add to the other BI parts. And if you looked at the graph of that in vector form, it should make a whole lot of sense. So if I had 6 minus 2i and negative 4 minus 3i, and I added those together, I could draw the parallelogram and draw the diagonal from the common initial point to the opposite vertex of the parallelogram, and that would give me 2 minus 5i. Now, I didn't draw that to scale because I probably would mess it up anyway, but does that make sense that that could be right 2 and down 5? Use your imagination. It actually does work out. I'm not drawing it that specifically and that well. So if we consider the complex plane, and if we called this the x and y axes, to go back into familiar territory, and if I were to draw some imaginary number that stops at x plus yi, so they're using x and y instead of a and b like I did, that's fine. And of course, what that means is that from the origin, we've moved x in the real direction, so that's a distance of x, and we've moved y in the vertical direction. That's how far we've gone in the I direction, is y. And we could talk about the angle that the complex number vector makes with the real number axis and call that theta. And so we might want to call the length of that vector r. This is kind of taking us back into familiar territory with x's and y's and r's. So, what are the relationships that exist? Well, from what we said before, we know that x is equal to r cosine theta. We know that y is equal to r sine theta. So we're getting into the polar version of this, where theta is the angle from the polar axis in the counterclockwise direction, and r is the distance from the pole. So these are familiar equations for us. We also know that r is the square root of x squared plus y squared, and that tangent of theta is y over x, and x can't be 0. So, if we start with the generic x plus y I and substitute for x with r cosine theta, plus substitute for y with r sine theta, you have what's called the polar form, or trigonometric form, of the complex number x plus yi. Now, a lot of people will write that with the r factored out as r times the quantity cosine theta plus I sine theta, which is a really good form for this, so I'd pay attention to that one right there. That's the biggie right there. So x plus yi is writable as r times the quantity cosine theta plus I sine theta. And that's how you'll change from rectangular form x plus yi into polar form, also known as trigonometric form, which is this r times the quantity cosine theta plus I sine theta. Now, there is an abbreviation of that. Notice that it's the same theta in both parts of that. And so the important thing is that it's r and then cosine and of theta and I times sine of theta. Of course, that theta is in two places, but the abbreviation for this r times quantity cosine theta plus I sine theta is called r cis theta, which means the same thing as the line above. And you can use this abbreviated form or the more expanded form. It kind of depends on what you're doing as to which form is more useful for you. But remember, if you see something in r cis theta, you need to know what it means. You need to be able to go backwards to r times cosine theta plus I sine theta to do some of the problems. That direction will be necessary to know. So please make note of that. We call r the modulus, or the absolute value of the complex number x plus yi, and theta is called the argument of the complex number x plus yi. That's a little bit of vocabulary to learn. And of course, absolute value makes sense because it's the distance from the origin, which is one of the definitions we use for absolute value. Is it's the distance on the number line from that point to the origin, or to 0. So that should make sense. Because sine theta and cosine theta have a period of 2 pi if we're in radians, or 360 degrees if we're in degrees, we're also often going to make it such that we have a restriction that we want theta to be between 0 and 2 pi if we're in radians, or between 0 degrees and 360 degrees if we're in degrees. Now, other intervals for theta would work for the argument if we wanted to use them. Those are kind of the common ones that most people use. And notice that r in this is defined to be not plus or minus the square root of x squared plus y squared, but just that. So in polar form of complex numbers, we're typically going to always have a positive r, which is kind of nice because those were actually a whole lot easier. All right, so let's do an example. They ask us to express that in rectangular form. Let me show you why you might want to know. If they had changed the directions and said 2 cis of 300 degrees, what is that in rectangular form? The first thing you'd want to do is rewrite 2 cis theta as 2 times the quantity cosine of 300 degrees plus I sine of 300 degrees, which is where this problem picks up. And so cosine of 300 degrees is 1/2 plus I times the sine of 300 degrees is negative square root of 3 over 2. And when you distribute the 2, you get 1 minus I square roots of 3. Please remember that you're supposed to know how to find the sine and cosine of these special angles like 300 degrees. 300 degrees is almost all the way around. It's 60 degrees shy of being all the way around. And so the reference angle here is a 60-degree angle. And so when we go to draw this in, since that's across from the longer side, that's square root of 3, and the short side is 1, and the radius is 2. So 1, 2 square root of 3. And then, of course, cosine is, and what I forgot to say is the distance is square root of 3, but because that's below the x-axis, the value is negative square root of 3. And then, of course, cosine of theta is x1 over r2, and sine of 300 degrees is y, negative square root of 3 over r2. That's how I got that. Okay, so that converts a number from trigonometric or polar form into the rectangular form. The a plus bi form is what I called it. They call it x plus yi form. So they have some steps for doing this that they suggest. Sketch a graph of the number x plus yi in the complex plane. Part of that is to go from rectangular to trigonometric. That theta is going to be problematic because you might find the wrong angle. It might be off by 180 degrees or something. So that's why they're going to suggest that you graph it first. Find r using the equation r equals the square root of x squared plus y squared. And then find theta using the equation tangent theta equals y over x. But be careful that you choose the correct theta for the quadrant indicated from your sketch. So let's do an example like that. Find that example. Here it is. Okay. So we're converting from rectangular to trigonometric. And let's start with a negative square root of 3 plus I, and the directions say use radian measure. That's important to know. What you're supposed to be using is radians or degrees. So pay attention to that direction. Okay, so what that means is, in their way of writing things, the x is the real part, what I called a earlier, and y is what I called b, the coefficient of I, which in this problem is an understood 1. So first thing I would do is sketch that in the complex plane. negative square root of 3, and I is somewhere in about that vicinity. And so I'm in the second quadrant, so that's kind of important to know that the angle I get may not be a second quadrant angle. I may have to alter what I have to make it correct. So okay, keep that in mind. Okay, so R is the square root of x squared plus y squared. Okay, negative square root of 3 squared is positive 3 plus 1 squared, which is 1. So that's 4. And so the square root of 4 means that R is 2. And remember, in this world, when you're writing the polar form of complex numbers, R will always be positive. So please be careful there. Okay, then to find theta, the tangent of theta will be y over x. And if I were thinking about that, with y being positive 1 and x being negative square root of 3, thinking back to trig stuff, this is 1, this is negative square root of 3, and so this is 2, and this is a special right triangle, 30, 60, 90. Opposite the one side, the short side, is the 30-degree angle, which is in radians, pi over 6. And so the angle we want to use is the angle that puts us into the second quadrant. So 180, pi minus pi over 6, that means that's 5 pi over 6. Okay, so that means that the polar form for negative square root of 3 plus I is R times the cosine of the theta we found in the correct quadrant plus I sine of that same angle. Oops. Which you can write in this form, or if you prefer, you can write 2 cis 5 pi over 6. Both of those answers are correct. Okay, now our second question that I'd like to look at, part B, is negative 3i, and this time we're using degree measure. Okay, so I'm going to start out by graphing this in the complex plane. You notice perhaps now how important it is that we label axes, because we all have all kinds of axes running around, and I need to know which axes you're thinking of when you are graphing these things. Okay, so that is going to graph at this place right here. There's a vector representation of it, and that means that the x part is an invisible 0, and the y part is a negative 3. Okay. So R is the square root of x squared plus y squared and that simplifies to be 3. And then the tangent of theta is y over x. And of course, that means when x is 0, we cannot rely on this equation. Tangent of theta equals y over x works as long as x is not 0. If it is 0, that means that the angle is either pi over 2, which is the same as 90 degrees, or it's 270 degrees, which is the same thing as 3 pi over 2. So I would just look at the picture when it's one of those two scenarios. Just look at the picture and think, okay, what angle is this? And what am I measuring in? That's either 3 pi over 2 or 270 degrees. This is 270 degrees. And so our answer to the question is negative 3i in rectangular form is the same thing as 3 cis 270 degrees. Or you could write it out in the long form. Okay, either way. All right, so what I want to do next is multiply complex numbers in rectangular form first. So if I had something like 1 plus I square roots of 3 times negative 2 square roots of 3 plus 2i, we're going to do that double distribution, which some of you call FOIL. So we're going to multiply 1 times both of the things in the second binomial. 1 times negative 2 square roots of 3 is negative 2 square roots of 3. That's what you would call first. And then 1 times 2i is 2i. That's what you'd call the outer. Then I multiply I squared roots of 3 times both things in the other binomial. So I squared roots of 3 times negative 2 square roots of 3 is negative 2i square roots of 9. I will simplify that in a minute. You'd call that the inner. And then finally, I squared roots of 3 times 2i is 2i squared times the square root of 3. And of course, I'll simplify all of that. And that would have been the last. So I didn't do it in your FOIL order. Curses foiled again. Sorry, bad pun. So simplifying, the third term I got, square root of 9 is 3. 2 times 3 is 6. So this becomes minus 6i. And I squared, if I is the square root of negative 1, that means that I squared is negative 1. So if we replace I squared with negative 1, that becomes subtract 2 square roots of 3. And then combining like terms, I get negative 4 square roots of 3 minus 4i. Okay, so not necessarily all that fun to do that way. So now what I'd like to do is do that same multiplication problem in polar form. Now you are going to think this first time through, oh my gosh, that's not better, that's worse. And it is, but we're doing it this long way first so we can see a shortcut. So this is kind of painful for a few minutes, but then it will become easy. And you'll go, oh my gosh, that is so easy. So the first thing we'd have to do is find the trigonometric form, or the polar form, for both of these. And I'm just going to tell you what they are. And we could go through that again if we need to. In fact, I might go back and do one of these. And the other one's pretty similar. So I'm just going to tell you this one, and I'll develop the other one here in just a second. Times something. So if that's what we are trying to get into polar form, we've done a couple of these already, so I'll be able to go through this kind of quickly. I'll do this off to the side. The x for the second one would be negative 2 squareds of 3. The y would be 2. So r would be the square root of x squared plus y squared. And so r would be 12 plus 4, 16, square root of that is 4. Okay, so that's what r is. And then tangent of theta is y, which is 2 over x, which is negative 2 squareds of 3. So the tangent of theta is negative 1 over the square root of 3. I should probably draw a picture of this to make sure I have the right quadrant. So x is negative, y is positive, is going to be, I don't have the scale right, I'm sure, but it's over here someplace where x is negative, y is positive, so we're in the second quadrant. And so if I were thinking of where that would be, using what we learned before, I could think of x as negative 1 and y as square root of 3. I'm sorry, I got that backwards. X would be negative square root of 3 and y would be positive 1. Yeah, it's y over x. I messed up. And of course that means this is 2. And so that is a 30-degree reference angle. And so the angle that we want is this one, which is 150 degrees. And so that's how you could go about doing that. And so this one would be 4, because r was 4, times the cosine of 150 degrees plus I sine of 150 degrees. I forgot a parenthesis back here. Put that back in. Okay, so the numbers 2 times 4 will be multiplied, and then we'll have a binomial that's cosine of 60 degrees plus I sine of 60 degrees times cosine of 150 degrees plus I sine of 150 degrees move over here, make sure I have plenty of room. 2 times 4 is 8 times, then I'm going to multiply those two binomials. I guess I could say using FOIL if you really want to. Anyway, that's cosine of 60 degrees times the cosine of 150 degrees. That's the first. And then the outer will be cosine 60 degrees times I sine of 150. So I'm going to call that I. I cosine of 60 degrees, excuse me, times sine of 150 degrees. Plus, now the inner product, I sine of 60 degrees times cosine of 150 degrees is I cosine of 150 degrees sine of 60 degrees. By the way, I'm just changing the order so that they all look kind of similar. May not end up liking that I did that, but that's what I did. Then multiplying the last, I times I is I squared sine of 60 degrees, sine of 150 degrees. You may be wondering, well, why am I not simplifying that? Well, if I did, I would be going back to the rectangular form, which is not really what I want to do. I'm trying to find a shortcut. So I'll be right back, just a second. All right, back. So at the last step, we had done the FOIL process, and now I'm going to rewrite these in a certain order on purpose. So just kind of hang tight as to why. It'll become clear in just a second. So that first one I like in front, so I'm going to keep it there. The next one I write, that I squared for the last one is -1, and I want to write that one next. So, nope, I'm sorry. Yeah, that's the one I want to write next. So sine is 60 degrees. And again, it's minus because I squared is equal to -1. Okay, so this one was first. This one was second. Then the next one I want to write is I sine of 60 degrees times the cosine of 150 degrees. And yeah, I changed the order in which I wrote those, and that was on purpose because of something that's coming up. And by the way, you're not going to have to repeat this yourself ever. So at least I hope you don't, because that means you've forgotten how to do the shortcut way. And that's not what I want you to do. So I'm just hoping you're following it more than anything else at this stage of the game. Plus I cosine of 60 degrees sine of 150 degrees. Okay, and so to complete that, that's the fourth one. Okay, so the two right here, there's an identity that we learned that looks like that. Cosine of something times the cosine of the second something, change the sign, sine of the first thing, sine of the second thing. Hopefully that's ringing a bell for you. That is the cosine of the first angle. The sign was changed, so plus the second angle. That's an identity that we learned earlier. Okay, plus, then I is a common factor in the next one, so I'm going to write the I. And these two, there's also an identity, if you pull the I out, for sine of something, cosine of the second something, keep the sign, cosine of the first, sine of the second. So I'm hoping you remember that one. That one is sine of the first one, keep the sign, plus the second one. And so that's 8 times the cosine of 210 degrees plus I sine of 210 degrees. Okay, the reason we went through all of this was not to go through all of this many times in your life, but to see a shortcut. So what I'd like for you to do is focus on the polar form of these numbers, what I'm underlining right now that we've multiplied, and tell me, looking at those original things I just underlined, where did the 8 come from? Well, it was the r from the first one times the r from the second one. Okay, that's how we got this 8. Then, my next question is, how did we get the 210 degrees? Well, we added the angle from the first one, which is the same in both places, 60 degrees in both of those places, and the angle of the second one. And what did we do with them? We added them. And of course, it's the same in both places. So I'm circling the cosine version each time, but it's the same for sine. So that is the shortcut for how you multiply numbers in polar form. So in general, here's the rule. If you're multiplying, say, let's call this radius 1, cosine of theta 1 plus I sine of theta 1. Oops, I forgot to write the I. Said it, didn't write it. And we're multiplying that by a second number in polar form. Let's call that r sub 2, cosine of theta sub 2 plus I sine of theta sub 2. That product will be r1 times r2 times the quantity cosine of theta 1 plus theta 2 plus I sine of the same angle, theta 1 plus theta 2. Okay, and in compact form, if you prefer, r1 cis theta 1 multiplied by r sub 2 cis theta sub 2 is r sub 1 r sub 2 so 2 cis theta 1 plus theta 2. And that's probably worth memorizing. These formulas are definitely worth memorizing. So I'm going to indicate that by putting a little star here. Okay, so let's do an example of that. We're supposed to find the product of 3 cosine of 45 degrees plus I sine of 45 degrees and multiply that by 2 cosine of 135 degrees plus I sine of 135 degrees. Okay, so that's going to be 3 times 2 times the product, times the quantity cosine of 45 degrees plus 135 degrees plus I times the sine of the same angle, 45 degrees plus 135 degrees. So that's 6 times the quantity cosine of 180 degrees plus I sine of 180 degrees. And that's the polar form of the answer. A lot of times you want to go ahead and simplify that to rectangular form. The cosine of 180 degrees is -1, plus I times the sine of 180 degrees is 0, and that simplifies to be -6. Yeah, that's fine. So that's how you can do that multiplication. Now, when we're going to divide, in rectangular form, one complex number divided by another one, what we have to do there is multiply it by a form of 1, and it will be, that form of 1 will be the conjugate of the denominator, so the sign in the middle changes sign from plus to minus here to become the conjugate. I bet you there's some of you who may have even forgotten that that's what you're supposed to do. Just saying. And so you multiply those two polynomials, and you get -2 square roots of 3. M in the numerator, minus 2i, minus 2i square roots of 9, so square root of 9 is 3, 2 times 3 is 6, so minus 6i, minus 2 square roots of 3i squared. I squared is -1, so that becomes plus 2 square roots of 3. And again, I'm not asking that you do this way because we're going to find a shortcut. And the denominator, when you multiply conjugates, you get a difference of 2 squares. Generically speaking, a plus b times a minus b is a squared minus b squared. So the square of -2 square roots of 3 is 4 square roots of 9. 4 times 3 is 12. And then 2i minus 2i times 2i is 4i squared, which is -4. This simplifies to be -8i over 16, which is -1/2 times I. And your answer in rectangular form needs to be in the form a plus bi. So you don't want I to be part of the fraction like we did with pi, like pi over 6. No, the I has to be behind, and the numerical part has to be written as a coefficient. So just so you get that right. If I were to write these in polar form for you, so I forgot to write the I. And I'm not going to go through this process again. I'm just going to show you the final result. This would be 2 cosine of 60 degrees plus I sine of 60 degrees. And -2 square roots of 3 plus 2i. In polar form is 4 cosine of 150 degrees plus I sine of 150 degrees. And then the answer, -1/2 I, in polar form is 1/2 cosine of negative 90 degrees plus I sine of negative 90 degrees. Now, if last time we multiplied the two r's and added the two angles, what's going on here? Can you see it? If you have the polar forms on the right, don't you see that 2 divided by 4? That part leads us to the 1/2 in our answer, and that 60 degrees, instead of add, minus, because we're dividing, minus makes sense here, minus the 150 degrees is our negative 90. Yeah, so consequently, the formula for this is r sub 1 cosine of theta sub 1 plus I sine of theta sub 1 divided by the second one, r2 cosine of theta sub 2 plus I sine of theta sub 2 will be r sub 1 over r sub 2 times cosine of theta 1 minus theta 2 plus I sine of the same angle, that is theta 1 minus theta 2. Or in compact form, r1 cis theta 1 divided by r2 cis theta 2 is r1 over r2 cis theta 1 minus theta 2. And again, these are important formulas. You need to know them. All right. So let's do an example of that. We're supposed to find this quotient and write the answer in rectangular form. All right, so using the formula that we just learned, that's going to be 10 divided by 5 cis negative 60 degrees minus 150 degrees, which simplifies to be 2 cis negative 210 degrees. So this is where you need to know that cis notation in the expanded form, because to go to rectangular form you need to think of this as 2 times the quantity cosine of negative 210 degrees plus I sine of negative 210 degrees. Okay, so I'm thinking of 210 degrees. Terminates right here. This is negative square root of 3. This is negative 1. That's 2. And so the cosine of negative 210 degrees is negative square root of 3 over 2 plus I times the sine of negative 210 degrees is negative 1 over 2, negative 1/2. Oops, oh, we're at the end of the rope here. And distributing the 2, you get negative square root of 3 minus I. Oh my gosh. What did I do wrong? Oh, I did positive 210 degrees. Oh, I see what I did wrong. Okay. Wow. My bad. Wrong graph. Negative 210 degrees. Let me try again. Negative 210 degrees is this way. And so that's our triangle. This is 1. This is negative square root of 3. And this is 2. And so what I did wrong was the cosine is negative square root of 3 over 2. However, the sine value is not negative 1/2, it's positive 1/2. That was my mistake. I apologize for that. Erase that little negative there. Get rid of that little guy. And so now all is right with the world. And so this ends up being, oops, I gotta get the brush down to the right size. Hold on. Okay. So this ends up being plus I. And that's our final answer. Sorry for that last minute mistake. That's the end of this section. I'll see you in class.